The last colligative property that we need to discuss is osmotic pressure. And this is the pressure needed to stop osmosis, which, okay, we need a picture and some better definitions here. But this is something that shows up in a lot of really like practical ways. I would say maybe especially if you're a pre-med, but also if you have a physical body, these osmotic pressure is important to you. So in practical terms, it's used a lot for IV solutions. We can calculate osmotic pressure with a dosage of a laxative. Um, right there will be a lot of ways in which we can use this or in which this matters. So we should talk about it. And to kind of frame it so that you really know what we're talking about, we need the pressure to stop osmosis. Let's talk about osmosis. Osmosis is flow of solvent through a membrane to equalize the concentrations. So, right, if I have this contraption, so I have this container that's got like two tall necks on it, there's a membrane in the middle. If I have a solution on one side and the pure solvent on the other side, what would happen when those solutions are in contact with each other, or the way we would think about looking at the osmotic pressure, is that the solution and the solvent would both start at the same height. In osmosis, right, this is the flow of solvent. So the solvent will go from the right to the left to try to equalize the concentrations. The solvent concentration, the concentration in the solvent is zero, right? So this is why like the solvent is going to keep moving in to dilute the solution to try to get it closer to zero. And that will result in a height difference. So the volume on the solution side is going to go up as the solvent moves over to dilute it, and the height on the solution, the solvent side, will go down because the solvent is moving out of this section. So that height difference, it helps you think about pressure. There's another equation besides the one I'm giving you that uses that height difference. But the osmotic pressure, which I have a capital pi on this because it's the letter that we use for osmotic pressure, it's the amount of pressure that you would have to push down on that solution side with to stop the solvent from flowing. So you can imagine more particles or higher concentrations, that solvent is going to like really want to come over to dilute the solution. So we'll have to put a higher pressure on it to stop osmosis from happening. So the equation has those things in it. So pi equals IMRT. So the pi is the osmotic pressure. I, this is my Van Hoff I factor. M, molarity. So we're using molarity again. R, it seems weird, but we're using the version that has atmospheres in it. We need liter atmospheres per mole Kelvin. Well, liters per mole, that's going to cancel with molarity. The per Kelvin, it's going to cancel with my temperature, which is also in here, and I'll be left with pressure units. So temp and Kelvin, so that it cancels. And this, I will get a pressure value out of this. So that pressure, that osmotic pressure, is the amount needed to stop osmosis. You've probably heard of reverse osmosis filtration. That's where you put a pressure higher than the osmotic pressure. If I use a pressure that's higher, that will push the flow of solvent in the other direction. So that gets the solvent to go over to the right-hand side. Now it's reverse osmosis because we are going to do the opposite of equalizing the concentrations. We're going to make it way concentrated on one side and absolutely zero on the other. So essentially, we've got all of what you would think of as impurities if you're trying to do reverse osmosis filtration collected on one side, and we've separated just the solvent on the other side. Okay, the way that that osmotic pressure will show up in this semester, other than calculating the osmotic pressure when you take a laxative, which we will absolutely do, um, it's used a lot to find molar masses. So I think I've brought this up a couple of times. If you remember from way back in 105, if you were listening to those videos, I said you can do an experiment to find the molar mass without knowing the identity. This is it. This is the experiment. So finding the osmotic pressure of a solution, it's used a lot to find the molar mass of a protein. You could use it to find the molar mass of an enzyme, right? Those are usually really big. We're not going to have the diagram of every single atom in it where we can go add it up on the periodic table, but we can find it with an experiment. So the problem we're going to do, we have an osmotic pressure. So this solution contains 5.87 milligrams of an unknown protein. It's 10 mils of solution, and we have an osmotic pressure of 2.45 torr at 25 degrees. Find the molar mass of the protein. And you would need to know that a protein is a non-electrolyte. So great, we're just going to use 1 for our I factor. Even better, we don't have to worry about it. So in my equation, I have pi. Well, I have pi in torr, so 2.45 torr. If I convert that to atmospheres, I get 0.00322 atmospheres, which I have to convert the pressure, or I have to find that version of R that has torr in it if I want to use it. I've converted to atmospheres because I'm using the 0.08206 liter atmospheres per mole Kelvin. I is 1. The temperature was 25 degrees, so that's 298.15 Kelvin. So pi equals I MRT. I mean, M is not the molar mass, but I can find M. It's the only thing I don't know. And maybe I can relate that to the molar mass. So find the molarity, which is 1.3176 times 10 to the minus 4th. And I'm going to write this as moles per liter because I know how many liters I have. I know the volume of the solution. So I know the molarity and I know the volume. So from that, I can find out how many moles of protein were dissolved in the solution, which is 1.3176 times 10 to the minus 6th moles of protein. Well, I know the mass and I know the number of moles. So normally we would say, I know the mass, I want the number of moles. How do I figure it out? Use the molar mass. Now I know the opposite sides of that, and I don't know the molar mass. But I do know how many grams are in a specific number of moles. Right? I know that 5.87 milligram sample, so 5.87 times 10 to the minus 3rd grams, was equal to 1.3176 times 10 to the minus 6 moles. So that many grams divided by that many moles will give me the molar mass. And when I do this division, I get 4.46 times 10 to the 3rd grams per mole. It's pretty big, but this is a protein. So I would expect a protein to have a big molar mass, and I do get that out of this.